So not to belabor the point too much, where our experiment tonight is going to be based on the Earth, okay, and an object falling near the surface of the Earth. We want to find out what G is, okay? So if I write this equation back up here, capital G, M, and let's just say that this object is M, and let's say that this is the mass of the Earth, M sub E. So that's M sub E. And we're going to use the radius of the Earth to this object to represent the distance of separation. Now, think about it like this. The radius of the Earth is so large compared to the object's center that it's negligible. So we're going to say R sub E squared. So from this equation implies that gravity is just equal to G times the mass of the Earth over R sub E squared. So that means we can rewrite F sub G like this. M times G. So you see it goes back to a familiar formula. And this is how we're thinking about it. That the numbers, this number represents the gravitational field. A way we can calculate the gravitational field of an object that possesses a mass. Not only a mass of the size of the Earth, but we emanate gravitational fields. So you have a gravitational field, I have one, but it's just so weak, it's so negligible compared to the size of the Earth that you know, people can't really feel it. The same with the sun. The sun is huge. The sun's gravitational pull is so great that it's holding the Earth in place. The Earth's gravitational pull is so great that it holds the moon in place and us, okay? So we're gonna do this calculation tonight. We're expecting this calculation to be something like, well, let me just go ahead and write down what G, M, and R are going to be. G, I want to go ahead and write this. I can write it in something darker. G is just 6.62 times 10 to the negative 11 Newton meters squared over kilograms squared. All right. The mass of the Earth is something like 5, I don't know, it's 6.2. Let me see real quick. What is the mass of the Earth?
The mass of the Earth is about 5.97 times 10 to the power of 24 kilograms.
All right, so we see that. So the mass of the Earth is 5.94 times 10 to the 24th kilograms. And we need the radius of the Earth. What is the radius of the Earth?
Let me check that. The average radius of the Earth is about 3,957 miles.
So we're going to use that 6.367 kilometers. I'm going to turn it to megameters. So 6.367 times 10 to the 6th meters. What is the value of the universal gravitational constant?
Let me check that. Here's what I found on the web for what is the value of the universal gravitational constant.
All right, it looks like, oh, there it is now here at the bottom. 6.67408 times 10 to the negative 11. Okay, 6.674. Okay, we were close. All right, that's good enough. So with these numbers, we're going to calculate G. What do we know G to already be? We know that G is approximately 9.81 meters per second squared. So we should get this when we do this calculation, or something close to it. Let me just go to a calculator here. And we're going to put these in. I think it was 6.674 times 10 to the negative 11th. And then, hold on for 1 second. So we have the universal gravitational constant there, and now we're going to multiply this times the mass of the Earth. So we're going to say 6, it was actually 5.97 times 10 to the 24th. And then we're going to divide this by the radius squared. So let's just put the radius in, and the radius is, let's go back. Yep, the mass was 5.94, and the radius is 6.37. 6.374 times 10 to the 6th. Oh, they put 0 there, so I need to put 6. And you know the bottom part is squared. Look at that. We end up with 9.807. So that's approximately 9.81. It's really good, okay?